Well, I'm going to take a try at filling in the lecture notes that I gave you on flavor interactions. It's going to be a little bit brief, or at least briefer than it was in class, but I'll hit the high points for you. So let's go ahead and take a look. We really are interested in how flavors interact with foods. If you go to a flavor company, you'll find that they will have probably several hundred different strawberry flavors. The same for other flavors. And why are there so many flavors in their library? Partly because different character. But a big important component is simply how that flavor interacts with the food. It just changes perception. The interactions change perception. So flavors have to be tailor-made for a food product. And so basically what we're interested in is we're interested in any kind of reaction that influences how much flavor is released from that food, how much is given up to be smelled. And so that's really what's important to us. Interactions that simply reduce the volatility of aroma compounds. Like I say, that really goes into or describes why flavors do taste different in different foods. Dealing and maintaining the same profile with changing ingredients is a challenge. You may change just one ingredient in your food, from one manufacturer even, to another manufacturer, and find the flavor performs differently. And I'm going to end up with the current protein trend challenges, because that's really the hot topic these days, protein in foods. So if we think of things that can influence flavor, simply pH. Have you ever tasted a nice tart chocolate and found it acceptable? Not really. Chocolate is that character of chocolate. The flavor compounds in chocolate are very dependent upon the pH of the food product. Aroma is influenced by pH because acids or bases become more soluble or less soluble in the food depending upon their pH. And this slide is just an example of that. An acid at low pH is protonated, and so it's not very water soluble. It wants to be out there being smelled. Low pH acids come through very well. At high pHs, it has a negative charge. It's more soluble, and so it's going to have less of an aroma. It really wants to stay in the food. And of course the same thing happens for basic compounds and just any type of amine as an example. Low pHs here, your molecule is charged and there's less aroma. Higher pHs, not charged and more aroma. So interesting relationship, just something as simple as pH. You know, we can think if we go to pH extremes, well, okay, we can have some hydrolysis, acid hydrolysis of fruit flavors. Some flavors like terpene-based materials, essential oils, they may degrade at low pHs. And of course, pH does influence reactions. The Maillard reaction, for example, Maillard reaction between flavor compounds and proteins. There's another effect, and that is pH effects on protein binding. And that can also be pH dependent. Protein binding of flavors. So we've got really many different ways that something as simple as simple as pH has an effect. So let's go on then and say a little bit about the major food constituents. And that would be lipids, carbohydrates, and proteins. Lipids are important. They're very important in influencing flavor. Think about the trend many years ago at this point where low-fat was the thing. Everybody was trying to produce low-fat foods that had a good flavor. And it didn't work very well. Now, these reactions are not chemical reactions, but they're more indirect effects. Flavors like to be in fat. If you have no fat in a food, that flavor is going to stick out. It's going to be volatile. Put a little lipid in there, and there's a place for the flavor to go into that fat or lipid. And so it's quite a challenge to get low-fat foods to taste just like the full fat because of that balance of the flavor compounds being absorbed into fat or not. This one here is just partitioning of aroma compounds. Diacetyl is very water soluble. Vanillin is kind of fat and oil soluble. And so basically this slide shows that if you increase the concentration in the oil and water is about 50-50 for vanilla or vanillin. But diacetyl is much more soluble in water. So as we increase the concentration of diacetyl, it stays in the water, the continuous phase, and it's available for smelling. So I guess just the difference between two compounds. There's some notes at the bottom of that slide. Example of an effect, vanilla flavored yogurt. Maybe you've got this formulated just perfectly for a yogurt, and you say, oh, I want to use that vanilla flavor in ice cream. What you would find as the vanilla note is lost. It simply goes away because your ice cream is high in fat. Vanilla loves to be in that fat. It's simply not going to be sensed without going to high concentrations. And so if our flavor was a combination of vanilla and diacetyl, vanilla buttery, basically the vanilla would go away. Think about this now. That's two compounds, but think about 20 compounds or 30 compounds that are all different. Some will like the fat and disappear. Some won't like it, and they'll stay there. And so we end up really having a change in intensity and change in character. This slide, I'm just going to say a little bit about it. And this is where we put diacetyl into aqueous systems with varying amount of fat, or limonene, or propanol, or heptanoate. Again, as I've said, diacetyl, water soluble, not really influenced much about fat content. It's pretty much the same. And that 1,000 over there says what you will smell, kind of. So your odor character from buttery stays pretty constant until you get to higher levels. Limonene, which is in essential oils, drops off with 0.1% oil. Look at 1%. It's probably 1/5 the strength or less, just with 1% oil, where diacetyl stayed there. So they're nice examples of how flavor changes. So the idea that fat influences the flavor level needed, and it also will change the character of that flavor because of this imbalance that we get. If we think about, is the flavor intensity character changed by putting the fat into an emulsion or just letting it sit with two separate phases? There's really no significant effect on that. Basically, the same amount of fat is there, and so we're going to get the partitioning of the flavor into the fat, whether it's in little bitty droplets or whether it's just sitting as a layer on top of the product. Really, there is no effect. It's based on, the effect is based on the total amount of fat in the product. So when we look at this, good chemists, good physical chemists, they could come in and do the partitioning and the mathematics, and they could tell you exactly what's going to happen to a flavor based on, like I say, pure physics partitioning. The problem is we can't necessarily change that balance. If we have a natural flavor from nature someplace, all kinds of different chemicals, well, we're going to put the flavor into a food that's going to become imbalanced. We can't go back to the plant and say, well, now you got to change your composition. You instruct the plant to reformulate its growth and hormones and whatever else. And so we can understand this, but we cannot fix it necessarily. If we have artificial flavors, we can do a pretty good job. But natural flavorings, plant extracts, it's a problem. And there's another unknown too, that our happiness, satisfaction with a flavor, it may just not be what we perceive as a taste or as an aroma, but there also is some work suggesting that there may be a fat receptor on the tongue. There's another one maybe in the gut that says, hey, I'm getting what I expected. I like that fat. I like the calories. I like that flavor. And so there's a problem here too, that we may be able to deliver what we should, but we're not happy with it yet because the brain says there's a mismatch here. You give me something that should have richness and fullness and it doesn't. I'm not happy. And so the question is, how do we fool the brain to think it should be happy? Well, that's number one. That's the easy one. If we look at interactions with carbohydrates, we look at one or the other effects. There's a direct effect where we may get a chemical interaction, chemical bonding of flavor to a carbohydrate. Otherwise, the carbohydrates may change the system. They may change the system to be, if it's a water system, adding sugars may make that water more hydrophilic or hydrophobic, a more suitable place for different flavor compounds. Or in fact, the carbohydrate may form a dry product, and nothing's going to leave that dry product until saliva, until it dissolves. So it can be a physical effect, changing the system to like the flavor compounds more or less, or it can completely interfere with any release until you put it in your mouth and chew it up. So different effects. All different types of bonding are potential. Again, it depends upon what's your flavor and what's your carbohydrate. If we kind of look at the idea of physical effects, does the carbohydrate provide some physical barrier to the release of a flavor, to smelling? Well, then we get into viscosity effects, or maybe we form a gel, so that's kind of a solid. So two different areas here. So if we start off with simple sugars, small amount of sugar, 5 to 10% sugar in a beverage, kind of balances, rounds out, completes the flavor. It may be necessary. When we think about fruits and all fruit flavors, they're typically sweet. If we would simply give someone just the flavor, the aroma, without sugar, and oftentimes without tartness, it wouldn't be right. So some sugar helps us, completes what our brain expects. If we look at lots of sugars, then it can be a different effect. If we go to high levels of sugars, you may find that the sugar tends to solubilize the flavor, keeping it inside, or maybe salt it out. But salting out, I really don't think we get to that level. So I like solubilizing, not salting out. But again, keep in mind, this effect is not uniform across all flavor compounds. And so we can change the flavor intensity, we can change flavor character. And there is some dependency upon whether or not a sugar is a monosaccharide or disaccharide, with monosaccharides having the greatest effect, of course. High potency sweeteners, I mentioned that about diet beverages. Diet beverage, Coca-Cola, Pepsi-Cola, all of the companies said, hey, we're going to take sugars out, we're going to put high potency sweeteners in, they're going to be the same. And they weren't. They weren't. People didn't like their high sugar products when you changed to high potency sweeteners. Or if we don't say they didn't like it, they changed, the profile changed, the character changed. It wasn't what they were expected. I personally like high potency sweeteners. I like colas, whatever, that have high potency sweeteners. Sugared, I don't care for. And we kind of say, well, okay, where does this effect come from? Is it somehow physical, chemical? Is some kind of a binding effect or solubilization effect? Is high potency sweeteners working differently with our receptors for sweet in our mouth? And so this is what's messing up things? Or in fact, is it something that happens in the brain? No, I'm sorry. That artificial sweetener, high potency sweetener, just isn't sugar. I'm not okay with this. So, again, where does this happen? I spent a little bit of time with this slide, and I basically pointed out I don't believe it. They are saying different compounds are influenced by aspartame, sucralose, or acesulfame-K. And the levels of aspartame and the other high-potency sweeteners, they're so low. They are not going to influence the volatility, especially increase the volatility. It's inconceivable how they can do that without significantly changing the hydrophilicity of the aqueous solution. That's not going to happen at 100 parts per million or 1 part per million. So I don't like the work. This is just an example of trying to adjust the flavor profile of a classic beverage. You'll see it there. A light beverage, one sweetener, and then the adjusted one where there's multiple sweeteners, multiple high potency sweeteners. And that's kind of the direction we're going. We typically are using now a couple of high intensity sweeteners rather than a single one. Aspartame does have a free amino group. It will react with your flavor compounds, and that is particularly a challenge for using aspartame. None of the other high-potency sweeteners have free amino groups, so aspartame is not used in thermal applications, and even some longer-term shelf life studies that are not thermal applications. It's reactive. There are some off-notes that come from high-potency sweeteners. Cyclamate, for example, has been found to be an off-flavor degradation in orange soft drinks. We've studied chewing gum, aspartame sweetened chewing gums, and found we will lose the flavor very quickly there as well. So it's interesting. It's certainly a challenge. If we move up to complex carbohydrates, starches, and gums, basically if a material gives viscosity or forms a gel, it increases the flavor need. And why is that? Why would making something more viscous or a gel increase the flavor need? And there's been a lot of hypotheses out there about, something that's viscous doesn't spread in your mouth. It's not as much surface area for release of flavor. Or if it's a gel, we got to break down the gel, and that takes some time, so you got to put more flavor in. But the work down here in this slide from Deborah Roberts really shows something that I think is much more relevant. And that is that certain compounds, like hydrophobic compounds, really like sugar-sweetened beverages. Sugar in water is more hydrophobic than water alone. So when we start adding sugar to the solution, we make it solubilize your flavor compounds, such as alpha-pinene, better. It's not released, so we need to add more alpha-pinene. If we look down there at vanillin, it really doesn't matter if sugar is present or not, because vanillin is both water-soluble and fat-soluble. So, again, little effect of whether you thicken with sucrose or in CMC. They would have only a minimal effect, but sucrose has an effect of making the water a more suitable environment for flavor compounds. They want to stay in the water, sucrose mixture, and so we need more flavor. There's some work, sensory work that's been done, basically saying that sucrose has a greater effect upon flavor release than carboxymethylcellulose or guar gum, for example. That's, as I said, CMC and guar really don't change the solubility, the hydrophobicity of your system. A texture effect, yes, some people basically have been looking at different gel strengths, for example, and they find that oftentimes there is an effect. Sometimes there isn't. It depends upon what type of material you're using to give viscosity or gel formation. This is an interesting one. This is looking at solutions from 0 to 2.5% pectin, so that would be very, very liquid, that's water, to quite a gel, or a viscous solution, I should say. And looking at the effect on basically the release, the sensing of each of these flavor compounds had been studied. And for the most part, analytically, there's really no difference going from water to a viscous solution. Only one compound, and that was a very hydrophobic compound, actually saw an effect. So if you look at it instrumentally, we're not seeing effective viscosity. And so I think I got a slide coming up here. This is the one I like, in the sense that panelists were given a whey protein that had an aroma compound in it. And so what they did is they used a mass spectrometer, sampled your exit breath, and this panelist was given this whey protein gel. And these gels varied from very weak gel to very strong gel. And simply the machine monitored how much aroma is each person being given, and as a function of the gel strength of the system. In our instrument, slide A, or part A on the right, said there's really not a significant difference in aroma release from these gels. But the sensory panel said there is a real difference, and so that's interesting. So why does a sensory panel say that a very thick gel is much less flavor than a very thin gel? That's a fascinating one, because you're given the same response. I shouldn't say response, you're given the same stimulus, and it doesn't matter. This is another one that shows, this is sensory for lemon flavor, and this is now gels that have been made. And again, the harder the gel, the less intense it was perceived. So fascinating. Again, if we would go back to instruments, we'd find there was probably no difference in stimuli. And so, theoretically, we said, oh, it's break down the mouth, what's happening binding to a polysaccharide. And really, we've more or less come to the opinion this is a brain effect. People have learned that something, one way or another, they've learned that things that are viscous or gelled aren't as strong in flavor as those that are less gelled. And so that's fascinating. This slide, basically 38, says, well, there were a couple of gels that were different from the norm, and that probably is where we're getting some kind of chemical interaction, like pectin or alginate, reacting with the flavor itself, probably by covalent bonds. So in some cases, we will eliminate our flavor through chemical bonding, not just physical. We don't have much information. Modified starches, gum acacia, alginates, locust bean. We really have very little data on how our gums will influence flavor interactions. Starches have been looked at pretty well. This is an old piece of data, sensory data, where they studied different alcohols, aldehydes, ketones from a sensory standpoint. And alcohols had a greater effect on intensity of flavors than the equivalent aldehydes. Aldehydes had a greater effect, interaction with the system, than ketones, and so on. Amylose was much more important in binding than amylopectin. Of course, that is understood because amylose forms an alpha helix. Flavor molecules can fit in that alpha helix and have come up with a flavor effect, flavor binding. And that's basically explained in this slide. This one that interests me too, though, and this is looking at different flavor molecules when they've been put into a raw starch solution, heated up, and then cool, add the flavor. Maybe I said that wrong. So gelatinize it, add flavor. Then see what happens to that flavor over 1 hour. And you find some molecules, such as ethyl acetate, decreased very little over that hour. But something else down here, for example, hexanol, hexane 1-ol, that's this one, had a major effect. And so some compounds were bound very tightly by that starch, other ones only partially bound. So again, think of it. You've got a flavor, it's nice and balanced, you put it into the food. oh, this one gets released. Oh, this one isn't released. So it really changes the intensity and character. It's also been working, say, gelatinized starch versus non-gelatinized. The cooling process and so on is important. We didn't do anything with cyclodextrins. So let's go on to our last topic. That's flavor interactions with proteins. And kind of as a beginning, if your protein makes a gel or makes it viscous, we're probably going to need more flavors. And so that's kind of in the same category as carbohydrates. But proteins are much more reactive. We got those amino acids, and we have a whole host of amino acids that could chemically react. And so we're really interested in that. I skipped protein structure, but again, this is looking at all the side chains of these amino acids. Lots of opportunity for chemical reactions to occur with your flavor. And so historically, we've kind of talked about, well, proteins will fold, their conformation structure, they fold over, they'll kind of create hydrophobic pockets, we'll have ionized pockets and so on throughout a protein once it gets done folding. And those nice pockets are great places for flavor to go to, kind of hang out there and not be released for sensing. And that's kind of what we've thought about. And I say this is the old view for the last 40 years. Been looking at these reversible reactions, and there's a list of them here. And this is what people have said is important. We're down here now, and basically finding out, man, there's covalent linkages that are important to us. And these are the ones that are much more important than these bondings above. So for 40, 50 years, we've been going with this top section, when in fact, this bottom section has been really important to us. We've known that sulfur reacts with protein. So we got sulfhydryls on our protein. Yeah, they'll react with disulfides and so on in flavors, but that's not the biggie. We've known also that just from a sensory standpoint, that flavor compounds, their sensory thresholds are much higher once you put them in protein. This is an example of these chemicals will have sensory thresholds 2 to 5 times. We need 2 to 5 times more flavor to be sensed when we put it in a 2% soy protein versus pure water. So we see major effects. And again, by old thinking, we've done some sensory work and found soy really a big problem for binding flavors. Gelatin less so, ovalbumin less so, casein less so, corn not. But that's not the fascinating thing. There's some old work by Arthur Hansen though that does again give an idea. Here's sensory vanilla intensity, arbitrary set in value over here. And so this is no protein in solution. Looking at this vanilla intensity, we add vanilla to water. Okay, that's our benchmark, our starting point. 0.125% casein or whey protein. Look at how much the flavor dropped off. Go to 0.25%. Go to 0.5%. We see a very rapid decrease, and much more so in whey protein than in the casein. So we're getting bonding. We're getting binding of vanilla, vanillin specifically, to the protein. 1996. Never documented how, where, or why. Well, that's interesting. This is just one that shows how much is free, how much is bound. Some compounds have lots of free and binding doesn't tend to go up with concentration. Other compounds, you increase your concentration slightly, most of that ends up being bound. And this is just looking, here's the native protein, denatured protein, more denatured. The more denatured, the greater the binding, the greater the effect on flavor. And so that's an interesting one. So there's your protein denatured by heat, acid, alkali, agitation, solvent. It will influence how the flavor performs in the system. So this also is one thing, and I'll skip the other ones because I didn't say about them. And this is looking at how aspartame reacts with cinnamic aldehyde, cinnamon flavor, in chewing gum. So this is actually plotting the sweetener, aspartame, but we'll have exactly the same plot for the flavor because the flavor interacts with the sweetener. 20 degrees centigrade, no flavor. The aspartame is reasonably stable. If we add flavor to it, what happens? 20 degrees. Look at the loss of our aspartame, corresponding loss of flavor. Here it's flavor in 35 degrees. So aspartame flavors very chemically reactive. Let's go on. I want to spend some time with what I call New World understanding. And that's where we are today. And this work tends to be done in our lab, and it's done by Vidi. And this is Amanda Sia. Amanda did an undergraduate thesis program, honors program. And so what she did is she made different, well, I didn't have the formulation. She made different high-protein bars using whey, soy, rice, or pea protein, added flavor compounds to it during the making process, immediately when made. She took a sample, analyzed it for flavor compound in each of the 4 different bars, and that's time 0. 1 week of storage. What's happened to the flavor? 2 weeks, 4 weeks. Your flavor was gone from the pea protein before 1 week of storage. It was all tied up, chemically bonded to the protein. There was no flavor contribution. In some of these other ones, they dropped about 50% in flavor in just 1 week. And down here, look at what levels. Basically, your flavor is disappearing because it's chemically bonding to the protein. This is benzaldehyde. Pea protein wasn't included in this experiment, but it's the same kind of thing. Here was time 0, and 1 week, 2 weeks, 4 weeks. In this case, the rice wasn't very reactive. But what happened with our whey and what happened with our soy? The flavor got bound fairly quickly over time. And Vidi has worked out a mass spectrometry approach to actually measuring these chemical interactions. And a mass spectrometer can actually take and measure the mass of a protein, and if it covalently bonds with a flavor molecule, it will now see the protein plus the molecular weight of that flavor molecule. So you see a second peak that basically reflects the protein plus the flavor. So we can actually get a mass fingerprint so we can monitor chemical reactions. We worked with beta-lactoglobulin. Low molecular weight works for us in mass spectrometry, and it's really well characterized and has all of the reactive amino acids we need. And so this is what we see if we look at beta-lactoglobulin. Here's our mass of beta-lactoglobulin, 18,276. Some oxidation here we find as it's secreted and as we isolate that protein, there is some chemical reaction. Interestingly, for one way or another, lactose has been added onto that. So here's our protein, and there's a lactose covalently bonded and a second lactose covalently bonded. So this is our normal profile of the protein isolate we prepared. What happens if we start putting a flavor in there? So here's our pure protein again with protein, lactose, lactose. Here's our protein, lactose, lactose. But a peak is showing up right here. It is exactly the mass of benzaldehyde. So they're starting to find a shifting of here to here. That's after only 10 minutes. Here's after 6 hours. And so these 2 peaks that were tiny, there's a tiny peak here, let's go here and here. Now they're almost equal on reacted versus 1 benzaldehyde added to it. So it's we're starting to really see a lot of chemical reaction in this system. And this is reacting beta-lactoglobulin allyl isothiocyanate. That's more of a garlicky note. And actually there's no unreacted protein. Well, no, I guess there's a little bit. How's that? This peak here has been shrunk to this, and all these other peaks are appearing. because now these all have some allyl isothiocyanate reacted with it. Here's diacetyl at pH 4, 6, and 8. Diacetyl at pH 4, small reaction, small reaction. pH 8, much, much more reaction. And so that's what we'd expect. It's the Maillard reaction. Higher the pH, the more the reaction. Other studies Vaidy has going, looking more at effective pH, effective concentration, denaturation. He wants to know where in the protein these flavor molecules are chemically added. It's really a fascinating study. You know, today these are some of our common flavoring materials. Lemon, cherry, watermelon, grapefruit. You know, every one of these flavors will have reactive chemicals that will be chemically bonded onto protein. So when somebody asks, I want a lemon-flavored high-protein bar, lemon-flavored high-protein beverage, forget it. Citral is the flavor compound. It's going to react with your protein, and it's going to be turned horrible in no time. Out of all these choices, this is the only one, methylantranolate, Concord grape. It doesn't react. So the idea of thinking we're going to have something beautiful and stable, it isn't going to happen unless we can find ways to block or use flavors that don't have chemical reactivity. It's a fascinating area. Lipids. So in summary, lipids we understand we can compensate to some extent for. Carbohydrates we partially understand. Unfortunately, no one's studying this anymore. They've kind of given up on it. But protein, we're really making some headway in terms of understanding what's happening and why. And hopefully the goal is to find a way to change reactivity of the materials we want to measure. It's a relevant area. It's an extremely important area when we try to deliver high-protein foods, for they have to be enjoyed. The flavor has to be acceptable, and we're just not there. And we have some challenges ahead. Well, with that, let's call it quits. I went through it fairly quickly, but I wanted to get this to you, so I will stop here.